Hello everyone and welcome to this AWS Online Tech Talk on Amazon Aurora. My name is Aditya Samant. I'm a Senior Database Specialist Solutions Architect here at AWS. I'm primarily focused on Amazon RDS and Amazon Aurora platforms and work with several databases during my day-to-day work with our customers. Today, we will talk about Amazon Aurora and what makes it an ideal choice when you're thinking of an open source relational database. We will show you why Amazon Aurora is the gold standard for deploying open source databases in the cloud. So to that end, we will take a closer look at Amazon Aurora and look at the fundamentals. We will see the storage subsystem that makes Amazon Aurora so special. We will look at several key innovations that sets Amazon Aurora apart from its competition, and we will even see a demo on some of the latest innovation. If you have any questions, please put them in the chat box and we'll respond to them as soon as we can. All right, let's dive in. So what is Amazon Aurora? First and foremost, Amazon Aurora is a relational database. It does not compromise on any relational database contracts and provides all the asset properties that you expect from a relational database. Aurora combines the speed and availability of the commercial databases while also keeping the simplicity and cost-effectiveness of open source databases, which means there is no licenses to manage and no licensing cost. There are no additions to worry about because Amazon Aurora offers all the advanced features right out of the box. There is no additional cost to simply use a feature, unlike some commercial databases that will charge a la carte for simply enabling a feature. Amazon Aurora is compatible with two open source database engines. You can choose either MySQL or PostgreSQL. This means the code you wrote for either of these databases will continue to work with Amazon Aurora without making any changes. You can use the same applications, the same operating system, the same drivers. There will be no change needed. All of this comes with the AWS promise of simple and pay-as-you-go pricing. So what about administration of this Aurora database? Well, Amazon Aurora is a managed database service, which means we take care of all the monotonous, undifferentiated heavy lifting for you, like installation and patch management and scaling and high availability setup, monitoring, backup, recovery, security, failover and failback, and more. This makes you, our customer, free to take on higher value tasks like application design, schema design, query design, and lets you focus on what matters most, which is innovating in your business. Now, sometimes folks who are new to AWS ecosystem ask if Amazon Aurora is used by large enterprises. The answer is a resounding yes. Aurora has been around for years, and it has been in use by thousands of our customers on a day-to-day basis. Amazon Aurora is the fastest growing service in AWS history. Aurora is so popular that it is used by 3/4 or roughly 75% of the top 100 AWS customers. This slide shows just a fraction of these customers who are using Aurora for their day-to-day and mission-critical database workloads alike. All right, so let's dive in and take a look at what makes Aurora tick and some of its fundamental building blocks. Before we look at the Aurora architectural improvements, let's first consider the challenges traditional relational databases face. Relational databases have existed for more than 40 years now. And over the years, we have found that the database performance is all about I/O. The faster the I/O, the faster the database performance. Increasing the I/O bandwidth and decreasing I/Os consumed will greatly improve the database performance. So traditionally, this is achieved by making storage local to the database, and that reduces I/O bottlenecks. While this can be a very effective way of achieving higher performance, it also introduces scalability and availability challenges. The challenge of making storage local by attaching it to the compute is that the compute and storage have different life cycles. They can fail independently of each other, and they may need to be replaced independently of each other. They may need to be shut down and restarted for patching. They need to scale up and down independently. Now, this is a significant challenge in traditional databases. So we innovated in this area, and Amazon Aurora decoupled the compute and storage, which helps us achieve much higher levels of scalability, availability, and durability compared to the traditional database approach of attached storage. So let's dive a little bit deeper into the storage architecture of Amazon Aurora and see what we mean by this decoupled architecture. Amazon Aurora has a purpose-built, lock-structured, and distributed storage subsystem under the covers. So by lock-structured, we mean that we only write transaction log pages or the delta changes to the storage. We never write any data pages to the storage, which also means we never have to do expensive I/O operations like checkpointing. We asynchronously rebuild the data pages in the background directly on the storage nodes. Storage volume gets striped across hundreds of storage nodes. The bottom right part of the slide represents the storage nodes in orange. These nodes are machines with processing power and memory with locally attached high-speed NVMe SSDs. The database doesn't know the intricacies of the storage. To the database, it is simply represented as a cluster storage volume. This cluster storage volume is multi-attached, which means that it gets attached to the readers and the writers at the same time. And we'll look at this in detail in upcoming slides. We also continuously back up and stream the data and log pages from the storage volume to S3 for additional durability. As a part of the distributed storage architecture, we replicate the data 3 ways. Each page is replicated across 3 availability zones with 2 copies in each availability zone. This helps Aurora survive failure of an entire availability zone plus an additional failed node. We segment the storage into 10 gigabytes of protection groups, and each protection group is further made up of 6 10 gigabyte segments. These are the 6 copies of replicated data we referred to earlier, 2 in each availability zone. Amazon Aurora storage scales automatically in 10 gigabyte increments up to a maximum of 128 terabyte size. It is also worth noting that the storage not only scales up automatically, but as you delete and clean up objects, the storage will also scale down automatically, making it highly elastic and very cost effective. So you may be wondering how Amazon Aurora avoids write amplification. As in, since Aurora is writing 6 copies on each page write, that will obviously amplify the write significantly, right? And that may cause write performance issues. Well, there are 2 things that Aurora does that makes writes efficient. First, Aurora only waits for 4 out of 6 copies of data to come back before it acknowledges writes. So the rest 2 can be written after the acknowledgement. Second, Aurora only ever writes transaction log pages, never writes any data pages, which significantly reduces the amount of data that gets written on the storage, reducing the amount of written data even further. So we'll dive a little bit deeper and show I/O profile comparison in upcoming slide to clarify this point further. Amazon Aurora storage provides exceptional durability. Let's see how. The distributed storage uses a quorum model for each read and write. Each write is broadcasted to 6 nodes at the same time, and whichever 4 nodes that come back first with an acknowledgement, we consider that as a successful write. If there is any corruption or missing data, the storage volume can rebuild itself as long as the 3 out of 6 nodes can provide a quorum. For reads, we don't need a 3 out of 4 quorum. We can read the data from any of the 6 nodes that have durable data which can satisfy the current read request, thus avoiding read amplification issues due to the quorum model. This distributed architecture not only protects against AZ+1 failures, as we discussed before, but it's also self-healing. It rebuilds failed segments automatically, and it's also able to rebalance hot storage nodes to provide added performance. The storage tier uses a peer-to-peer exchange protocol called Gossip Protocol for rebalancing and self-healing needs. So this is the protection against failure that we talked about before. As you can see on the slide, an entire AZ plus one node going down will still keep this cluster running. The distributed and decoupled storage technology lets us further innovate in how Amazon Aurora scales. Amazon Aurora can have up to 16 nodes in a cluster, one writer node and up to 15 reader node. First node will always be the writer node. Storage volume is shared across all of the nodes, readers and writers. Readers open the volume in a read-only mode, which can be verified by looking at the database-specific flag depending on the database engine you're using. The log structure storage is incredibly efficient at replicating the data, and the replication lag between writers and readers is roughly 20 milliseconds. When you create a multi-AZ Aurora cluster, meaning one reader and at least one additional, one writer and at least one additional reader node, you get an uptime SLA of 4 nines or 99.99%. So if you're wondering, how do my applications access an Aurora cluster? The answer is via the reader and the writer endpoints. When you create an Aurora cluster, you get a cluster endpoint, which always points to the writer node. This cluster endpoint is sometimes also referred to as a writer endpoint. This is helpful when creating applications which don't have to know the underlying cluster topology and will continue to point to the correct writer node even if there is a failover. We also create a reader endpoint which has the ability to round robin between all the reader nodes, giving you a managed ability to load balance your read requests without having to make any special code changes in your app. So keep in mind, you can create as many as 15 read replicas. So the reader endpoint actually gives you an ability, especially if you have more than one read replica, to take your incoming read requests and automatically load balance across these read replicas. You can even create a custom endpoint to support your specific app needs like analytics and reporting and automatically scale the number of reader nodes by applying a scaling policy. So the reader nodes actually give you this ability of horizontal scaling by applying auto scaling policy for these reader nodes. So here's an example of how the endpoints look like in an Aurora cluster. So here's the cluster name on the top. At the bottom, you can see there is a writer endpoint, and you can see the type of that as a writer instance. And then there's the other endpoint. This is the reader endpoint, and you can see the type as reader instance. So what happens if the writer instance fails for some reason? It could be a network issue, or it could be a hardware failure, or something else. How does Amazon Aurora respond? In case of a failure of the writer node, any surviving reader node can take over the role of a new writer. This failover is done automatically, and it does not need any intervention or manual steps. When the old writer becomes available again, it will come online as a reader. If you have multiple reader nodes, Aurora lets you assign a failover tier, so automatic failover can choose a reader based on the predefined priority. For example, if you have two readers, and you assign a failover priority as 0 to one of those readers and a value of 5 to another reader, then the one with the value assigned 0 will become the failover target. So you may be wondering, with all these changes and storage-based efficiencies, how does Aurora I/O profile look like when compared to a more traditional MySQL or Postgres database? A quick comparison of Community Edition of MySQL on the left and Aurora MySQL on the right using a standard 20-minute sysbench test shows us that Aurora MySQL is able to support 35 times more transactions while generating 7 times less I/O, which makes Aurora significantly more efficient in handling high-throughput transactional workloads. This is possible due to the distributed storage architecture that only ever sends transaction logs to the storage, thus significantly reducing the I/O activity going across the network. When you compare this to an RDS MySQL synchronous high availability architecture, you can see that there is an additive latency from point 1 all the way to point 5, in addition to the data and log and other metadata that has to be written to the disk. Same goes for Aurora PostgreSQL. In traditional PostgreSQL, as shown on the left-hand side of the slide, there are mechanisms put in place to recover from possible corruptions. And it can generate full page writes during a checkpoint or after a checkpoint. Since Aurora's storage subsystem uses quorum-based system to recover in case of a corruption, it does not need checkpoints, and it avoids the full page writes, and it is significantly more I/O efficient. Let's look at the Aurora read replicas. Aurora read replicas tend to be a lot more efficient at serving read requests when compared to a traditional read replica. On the left-hand side of this slide, you would see a traditional read replica. In a traditional database system, read replicas are serving reads, but they also have to redo all the writes that were done on the primary to stay synced, usually in a single-threaded way. This makes the readers only partially available for a read workload. On the right-hand side of this slide, you see an Aurora read replica. Because we are using physical replication in Aurora at the storage level, the read replicas don't have to redo all the transaction, which makes them a lot more efficient than, say, binlog or based logical replication-based replicas. And they are almost 100% dedicated to only read workloads. And they serve only your read workloads because they are not redoing all the transactions that were possibly done in a multi-threaded way on the primary, and then take it and do it in a replay it in a single-threaded way on the secondary. So to summarize, these architectural improvements mean that Amazon Aurora does less work, like making fewer I/O requests and minimizing network round trips, while being more efficient by asynchronously processing requests and reducing latency path. This results in a significantly more scalable database system when compared to the self-managed version of MySQL and PostgreSQL. Okay, so let's look at some of the key innovations that Amazon Aurora has done over the years. Now, what better way to start talking about new and innovative features than Aurora Serverless v2, which was made generally available in April of this year. Aurora Serverless v2 is an on-demand auto-scaling configuration, and it will automatically scale the compute needs to fit the workload. You will define the lower and upper bounds in terms of ACUs, or Aurora capacity units, and then Amazon Aurora will automatically scale between those defined ACU bounds as the workload scales. The compute capacity can scale up as well as scale down as the workload changes. Aurora Serverless v2 is able to scale in place and rapidly. We do this by taking a running database process and giving it more resources like CPU and memory, and that's how it's able to scale up instantly and, more important, non-disruptively. This is in contrast of the previous version of serverless, Aurora Serverless v1, which needed to find a safe point or pause for scaling. This is no longer the case with Aurora Serverless v2. We continuously monitor our compute fleet for heat management, and we are also looking for where the capacity is needed. When we know where the capacity is needed, we move the database instance from a busy host to idle hosts as needed, and we do this automatically. There is no manual intervention needed, or there are no database restarts needed. During this move, we will preserve the state of the database, like the session state, the variable values, and the memory state. The scale up is fast. We scale up in a fraction of a second, but we scale down slower intentionally. This is done so as to not evict the data from the buffer pool too quickly if you need it again. Let's see a quick demo of how Serverless v2 scales in practice. Okay, so in this demo here, what we're showing you is this is a CloudWatch dashboard that's going to track our ACU utilization. So we are going to do a flash sale type of application. So on this dashboard, what you see is at the bottom of the screen, you see an orange line. This orange line is the current workload. So the current workload is very stable. And then the blue line is the number of ACUs, or Aurora capacity units. Because the workload is stable and it's not needing any additional CPU or memory, we see that the ACUs stay pretty stable and they're not going up or down. Now, the limit that we have set on ACU is that the lower bound here is 1.5 ACUs, and then the higher bound is 9 ACUs. And as you can see that the workload starts to spike, the orange line is spiking, and as soon as the workload starts to spike, the blue line, which is our ACUs, immediately starts and catches up to that workload. So the ACUs are responding immediately so as to give enough CPU and memory capacity for that workload to satisfy. And now what I'm going to do is, because we don't have a ton of time to actually wait several minutes for this demo to finish, I am going to fast forward this clip. And then in this fast forwarded clip, you can still see that as the workload continues to go up, our ACUs continue to go up along with it. And eventually it hits the peak of 9 ACUs. By the way, this is a choice that we have made. You can go much higher than 9 ACUs. But here, since we have kept 9 ACUs as our peak, that's the maximum serverless v2 allowed the server to scale up to. But you can see that even after the workload basically finishes and goes back to its baseline, the ACUs are not immediately coming down. And which is what we want, right? Which is what we discussed, because we don't want the ACUs to immediately start to go down, which is going to cause all sorts of page evictions. And if later you need the additional ACUs, then you're going to have to scale up again. So we want to avoid this constant scale up and scale down. As you can see that eventually the workload stayed stable, and then the ACUs came down to its minimum limit, which was 1.5 ACUs. Let's take a look at what operational enhancements Aurora has done when it comes to backup, restore, and recovery. Amazon Aurora's decoupled storage also brings several added operational benefits besides improved performance. Near instant crash recovery is one of such benefits. Consider traditional database crash recovery. It involves several single-threaded operations like scanning for incomplete transactions and looking for last checkpoint. This can significantly delay database recovery in case of a recovery from crash. In case of Amazon Aurora, we have 10 gigabytes of storage segments which have their own redo logs. These redo logs are processed in parallel and in out of order. So in effect, the Aurora database recovery can be done parallel and out of order. Compared to the serial nature of traditional database recovery, this is significantly more efficient. Because the recovery is fast, Aurora is able to become available after a failover a lot quicker. Here are a few charts that show you our observation of Amazon Aurora failovers. What matters here is that the failover happens very quickly. These charts show you the percentage of failovers that happen in a given time frame, say 0 to 5 seconds or 5 to 10 seconds. We measured this over 35 days, and you have one data point along the x-axis for each day. In our fleet, we observe 30% of failovers were in less than 5 seconds, 70% were in less than 10 seconds, and 95% in less than 20 seconds. And effectively, 100% of failovers were happening within less than 30 seconds. Aurora PostgreSQL has a cluster cache management feature that improves application performance after failover. Let's take a look and see how this works. As we discussed earlier, you can designate failover tiers for read replicas. This means you can predetermine which node gets to be promoted to a primary if there is a failover. You do this by assigning the failover priority of 0 for a read replica. When the cluster cache management feature is enabled, we ship a Bloom filtered cache of replica buffer to the writer node. A Bloom filter is a space-efficient probabilistic filter that avoids duplicate sends from a reader to writer. On receipt of these cache blocks, the writer compares it with its cache and sends the frequently used buffers to the read-only node. So due to the cache optimization, if a failover occurs, the newly promoted writer has its cache warmed in advance, and applications accessing the new writer will not have to suffer the buffer cache warming penalty. Here's a practical example of cluster cache management in action. In this example, we ran a PG bench that was read-heavy, about 20:1 read-to-write ratio. We had 160 gig cache, so that's a fairly large database. At 600 seconds, we caused a failover. It took about 32 seconds for the database to recover, considering DNS propagation and all. But it took roughly 340 seconds for the database performance to reach the acceptable performance, which was 10 times as long. The acceptable performance is shown by the black line, and the blue line shows the baseline when CCM is not enabled. The purple line is the performance when CCM is enabled. Now you can see that after failover, the purple line catches up to the acceptable performance immediately because the cache is already warmed up. So this feature is pretty useful and dramatically improves performance and the user experience after a failover. Okay, now let's see how Aurora handles point-in-time restores. Aurora backs up your cluster volumes continuously and automatically and retains restorable data for the length of backup retention period. If you remember, we discussed storage segments during the storage deep dive. Backups are done by taking periodic snapshots of each segment. In addition, Amazon Aurora continuously streams the log pages to S3. This is done without any impact on the performance or availability of the database. This gives you the ability to do point-in-time restores for the database during the backup retention period. If you request a point-in-time restore, we take the latest snapshot and then we apply the log records to the segments in parallel and asynchronously making the restore very, very efficient and very fast. So for example, if you have defined your retention period to, let's say, 7 days, then we will keep the 7 days worth of backup and we will give you the ability to do a point-in-time restore to any point during those 7 days. And then we'll automatically age out the backups once the retention period is expired. So we know that Aurora is continuously backing up the data pages. But how does that managed backup restore experience look like? You get fully managed backup and restore with Amazon Aurora. You can decide backup retention period anywhere between 1 to 35 days, and Aurora will continuously back up your database while rolling the backup window forward according to your retention needs. This setup once mechanism will take continuous automatic backups and will allow you to do a point-in-time restore to any time during that retention period. The latest recoverable time is usually within the last 5 minutes from current time. In addition, you can also take manual snapshots, which will persist in storage until you choose to delete them. Now, this is a very important differentiation. The manual snapshots are not deleted until you delete them. Automatic backups are automatically aged out. So if you're taking manual snapshots, make sure that you're cleaning them up when you don't need them. Restoring a database is a simple point and click process. This can be automated via CLI or API. The time to restore varies based on the size of the database cluster to be restored. And at the end of the restore, you will always have a new cluster created. Now, there are times in every DBA's life when they wished that there was a magic wand that they could use to turn back time on the database. Well, with Aurora Database Backtrack, you have just that. Aurora Backtrack is a feature that lets you recover from database changes like unintentional DML or DDL operations by giving you a virtual rewind feature of sorts. With Aurora Backtrack, if you discover that an unintentional delete was performed, for example, You can backtrack the database to a point before that delete ever happened, and then continue from that point onwards. You have the ability to backtrack in place, and this operation takes a few minutes to perform. In this example, as shown on the slide, you have a continuous timeline at the bottom that is represented by the gray line from T0, T1, all the way up to T4. Let's say you made an unintentional change at timestamp T2 and realized that you wanted to move to a point before this change ever happened. You can do that using Backtrack and reset the database back to T1. This will make all changes between T1 and T2 invisible as if they never happened. When you're doing this reset, the entire cluster becomes unavailable and you see that the cluster is in a rewind state or a backtrack state. Similarly, if you realize at a timestamp T4 that another unintentional change had happened, then you can rewind back to T3, making those changes between T4 and T3 invisible and continue normal database operations after that. Now let's see what options we have for cloning and also for cross-region disaster recovery. A frequent need in enterprise database operations is the ability to clone a database. The reasons for cloning a database can be various. You can want it for testing, code changes, for patches, for upgrades, among other things. Traditionally, this means you have to restore from a database backup. Now, depending on the size of the database, this can take hours or sometimes even days. Fast database cloning is an Aurora feature that utilizes the decoupled storage architecture to make this process significantly faster. Fast database clone can be completed within minutes, regardless of the database size, which gives you a huge advantage when compared to traditional database restore process. This is possible because no physical copying of data ever happens. The cloned database uses the same storage volume as the source, and it only makes changes to pages by using a copy-on-change algorithm. Here's an explanation of how fast cloning works under the covers. On this slide, you see the source database on the left-hand side and then the clone database on the right-hand side. Initially, the clone database continues to use the same storage volume and the data pages as the source. But as the source database and the clone databases start to make changes, they start to diverge. For example, if the source database changed the page showed in orange, or changed the page number 4 showed in orange, then the clone database will make a copy of that page for itself, and then the source database can make changes to that page. Thus, it preserves the original page for the clone database. This is how copy-on-change process works. Given enough time and activity on both source and clone databases, they will continue to diverge and will end up having completely separate storages represented by orange and green colored pages on this slide. For cross-region DR setup, Aurora has a built-in feature we call Aurora Global Database. Aurora Global Database is a feature designed for globally distributed applications, allowing a single Amazon Aurora database to span multiple AWS regions. It uses physical replication to replicate across regions without impacting database performance, enables fast local reads with low latency in each region, and provides disaster recovery from region-wide outages. The underlying replication technology utilizes a replication fleet in both source and destination region. The outbound replication fleet in the primary region gathers delta changes from the database and sends it to the secondary region. The secondary region's inbound replication fleet receives these changes and then applies it to the secondary databases. Up to 5 secondary regions are supported as of today, and each 5 database regions can have up to 15 read replicas within those secondary clusters. Global databases are designed for high throughput since the replication happens on the storage level. Compute nodes are available for transaction processing and they don't need to do any sort of work for this specific replication. Our testing has shown replica lag to be below 1 second between East Coast and West Coast regions. Global databases also support a feature called write forwarding, which also allows applications in the secondary region to use the same endpoint for both reads and writes, while we forward the writes to the primary region, thus reducing the need to create VPN tunnels or having to manage multiple endpoints. In this example, we see primary Aurora cluster in the Ohio region in the middle of the slide. We can also see that the primary region has the only writer instance and then 2 reader instances. Oregon, Virginia, and Ireland are set up as secondary regions. They have multiple reader instances, and changes made in Ohio region get replicated to these regions continuously. In case you need to switch regions and flip the primary and secondary regions, it's simple console-based click-through operation. Okay, so let's look at why physical replication is important and the significant performance advantage it brings to the table. In this slide, we see the performance comparison between binary logs-based logical replication on the left and then physical replication for the global databases on the right. We tested performance of replication by stepping up load every 600 seconds. In both tests, we use R4 16x large instances. The red line represents queries per second, and the blue line shows the replication lag. As you can see, when using binlog-based logical replication, we were able to get roughly 40,000 queries per second, and then the lag skyrocketed to several hundreds of seconds, essentially unable to scale any further. The physical replication, on the other hand, was able to continue to scale seamlessly all the way up to 200,000 queries per second, which was the performance ceiling of that instance time for the test, while keeping the lag under a second. So you can see that the physical replication is very efficient and is able to scale seamlessly. Another important Aurora feature is the managed planned failover for Aurora Global Databases. This feature lets you automatically failover a global database cluster from one region to another and promote the new region as a primary. You can use this feature for testing your DR setup or relocating your primary region while maintaining full topology. Before this feature became available, you had to recreate the primary and secondary global database topology by completely tearing down global databases. This feature will facilitate zero RPO since we will stop all writes to the current primary while the secondary catches up, and then it will get promoted. Here's an example. Here, Ohio is the primary. We manually failover and promote it. When we do that, first Ohio writes are stopped. Then North Virginia catches up. Then other regions are attached to North Virginia. Writes are now available in North Virginia region. And you point your application to the new point and go. Fairly simple. All right, let's see what performance and monitoring enhancements we can expect from Aurora. So by now, we have well established that storage in Aurora is distributed across hundreds of storage nodes that have their own processing capability. So let's talk about another Aurora capability that takes advantage of the distributed storage and builds on top of it. We call this feature parallel query. Aurora is able to make great use of storage node processing power by taking your analytical queries, generally those that process all or large parts of a good-sized table, and runs them in parallel across hundreds or thousands of storage nodes. The speed benefit is usually in orders of magnitude. Parallel query, when used, also reduces network I/O, CPU, and buffer pool contention, so you can run a mix of analytical and transactional queries simultaneously on the same table while maintaining high throughput for various types of queries. In comparison, when not using parallel query, the database node has to pull all the pages into the memory, thus incurring additional network I/O and CPU utilization. Currently, parallel query supports filters, projections, expressions, and we continue to refine it and add more features as we go. Amazon Aurora is a managed database. So a common expectation is also to have a way to manage and assess database performance and find bottlenecks. Since Aurora is a managed database, the people working with it are not required to have deep database and tuning expertise. So to streamline performance management, we made a tool available that's super simple to use and available right there in the database console called Performance Insights. Cool thing about Performance Insights is that it is a single pane of glass for your database performance, which aggregates performance data like query performance, wait stats, along with operating system counters, which lets you correlate all of this information and find bottlenecks quickly. When you enable Performance Insights, rolling 7 days of performance data history is made available at no charge. Up to 7 days of aggregated performance insights are made available completely free of charge, but if you need to store data longer, you can do that as well. You will be charged for storage above and beyond the 7 days of free tier. You can store this data up to 2 years. So let's look at an example. On the top 2 graphs, the database load is broken down by wait events by default. This tells you the type of activity that is causing the database load. But you can also choose to break the load down by any other dimensions, like SQL or hosts or users. Below the database load chart, we see a list of top SQL statements running. This is also ordered by our core metric, database load or DB load. From this list, you can easily see which SQL is most responsible for load in the database and the type of activity that is causing each of those to consume load. Note that the colors tell you what kind of wait events are dominating. Example, number 4 is all CPU. You also might have noticed that some of these SQL statements have question marks instead of real values in certain places. This is because we normalize large number of very similar SQL, one that differs only by the values in their where clause, and we put them into buckets called digests, so we can characterize them here as a single logical SQL. This way, you are able to see the real impact of SQL in total. If you want to know what SQL comprising the digest looks like, you can always drill down into the individual SQL statements. This makes this tool very powerful for looking at and assessing the performance bottlenecks on your Aurora cluster. Next, we'll look at connection management enhancements that are made in Amazon Aurora. So we already know that Amazon Aurora offers multi-AZ for in-region high availability, and it offers 4 nines of uptime SLA. Failovers are super quick in multi-AZ configurations as we saw before. But what if you wanted even more seamless experience during failover and remove the dependency on things like stale DNS caching? That's where RDS Proxy comes in. It helps stabilize and reduce connections against the backend database, and it does that by using connection multiplexing and makes the database scale much better. Amazon Aurora integrates with several other AWS services, RDS Proxy being one of those services. RDS Proxy is a fully managed database proxy that makes applications more scalable, more resilient to database failures, and more secure. Let's see how. RDS Proxy fronts the database and accepts and pools all the database connections. In the backend, it intelligently reutilizes already established connections by using multiplexing techniques. This reduces connections against the database, which reduces memory and CPU load on the database server and also helps scale much better when application increases the number of connections to the database. RDS Proxy also has the ability to hold connections in case there is a failover in progress, and then release these connections to the new primary database in a graceful manner when the failover completes. In addition to this, when application uses RDS Proxy, it bypasses DNS and thus avoids stale DNS caching issues. This makes the failover recovery much quicker, and we have seen failovers happen up to 66% faster when using RDS Proxy when compared to regular DNS endpoints. In addition, RDS Proxy integrates with AWS Secrets Manager and lets you store passwords securely and even enforce IAM authentication if you wanted to. RDS Proxy also supports connection encryption to enable securely connecting to the database. Now, ever so often, you have to apply database patches. More often than not, when you apply a patch, it's also going to cause a database restart. Amazon Aurora has a feature called zero downtime patching that can help preserve application sessions during database engine patching. Without zero downtime patching, all application connections are broken during the database restart, and the application has to implement retry logic to reestablish connections. With ZDP enabled, Aurora can help preserve application sessions, and after the database restarts, the preserved sessions can restart seamlessly. Now, ZDP or zero downtime patching was only available for MySQL for the longest time, but just recently, I want to say just as early as last month, we also released this feature for PostgreSQL. So both Aurora MySQL and Aurora PostgreSQL support zero downtime patching now. So all the Aurora features we looked at were just a quick overview and not really an exhaustive list. Since we have limited time here today, I was not able to cover all and definitely not able to cover all in a lot of detail. Amazon Aurora has many more features like machine learning integration, database activity streams, enhanced thread and locking model, and I'm sure I'm missing a few here as well. So please reach out to us if you'd like to learn more or dive deep into any of these specific features. So in summary, Amazon Aurora takes advantage of the cloud-native features like the abundance of storage and compute. Aurora uses distributed, purpose-built, and lock-structured storage, which is kind of the secret sauce behind Amazon Aurora, which makes it so scalable. Aurora has an elastic architecture that scales the compute and storage up and down per workload needs. Amazon Aurora has built-in features like automated backups, multi-AZ architecture, global databases, and more that make it highly resilient to failures. Features like Backtrack and fast recovery, fast cloning makes it even easier to recover from failures. And recovery from failures can be further managed by using integrations to other services like RDS Proxy. Well, that concludes this session for today. Hopefully, this gave you enough information and helped convince you that Amazon Aurora is the gold standard when it comes to launching an open source based database workload in the cloud. I want to thank you so much for your time, and I wish you have a great rest of your day. Now, if there are any more open questions, please feel free to type in and we'll try to answer them now and as much as we can. Thank you so much.